Today we're going to talk about Lewis structures, the octet rule, as well as lattice energy. And so let's dive right into this. This is some information from general chemistry that we're going to be reviewing, so we're not going to spend a whole lot of time on it. But real quickly, we all remember that we have valence electrons. These are going to be our electrons involved in bonding for atoms. And so if we were to draw the electron configuration, or write the electron configuration, for example, of sodium, sodium has 11 electrons in a neutral atom, 1s2, 2s2, 2p6, 3s1 would be its electron configuration. Its valence electron would be this lone 3s1 electron that is lost when sodium forms an ion. Or if we were to draw the structure, the electron configuration, excuse me, of fluorine with 9, 1s2, 2s2, 2p5, these outside highest energy electrons would be our valence. And so our easy way to determine our valence electrons is valence electrons are going to be equal to our group number on the periodic table. Group number and these are for representative elements. So in group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A for the most part. Okay, those are going to be our valence. And we're going to kind of limit it to that. And so as we remember from general chemistry, our Lewis structures, when we draw Lewis structures, is we have our symbol and then we have dots placed around our symbol, and those are equal to the number of valence electrons an element has. For example, carbon. Carbon is in column 4A, and so carbon has 4 valence electrons. So we would draw them 1, 2, 3, 4, and that would be the Lewis structure for carbon. Oxygen being in group 6A, oxygen is going to have 6 valence electrons. So we're going to go 1, 2, 3, 4, and there's our 5th, and then there's our 6th valence electron. So we have 2 of these valence electrons which are paired in oxygen. Those 2 are paired, and then we have 2 individual electrons here and here, which we're going to be shared in a molecular bond. And that brings us to the octet rule. And the octet rule, of course, is going to be that atoms tend to gain, lose, or share electrons to achieve 8. Valence electrons. So, and of course, there's always exceptions to this, and we'll be talking about those more in the future. Hydrogen is one of the big exceptions, and hydrogen is after 2 valence electrons. And then there's also some other exceptions we'll be talking about shortly. Now, this idea brings us to ionic bonding now. And in ionic bonding, we typically see ionic bonding when we have a metal plus a nonmetal, as we know. We know we have opposite charges and things like that. We know we have very high melting points. And so let me give you an example of what's going to happen here in sodium and chlorine. So if we have sodium with its 1 valence electron and we have chlorine with its 1, 2, 3, 4, 5, 6, 7 valence electrons, it's a benefit for stability of sodium is to lose that 1 valence electron. And so it's going to transfer that 1 valence electron over to the chlorine. And then chlorine has 8, and sodium still, it normally has 11, but now it's back down to 10, so it has completely filled S and P sublevels. So what we're going to form is we're going to form a sodium ion, and then we're going to form a chlorine ion with its 8 valence electrons around it. Just like that, we'll put brackets on there to designate that. There we go, our charge there on the outside. Okay, I think I just jumped up there. Let me scooch back down. Okay, and the next thing we're going to talk about here is we're going to talk about lattice energy. And so we have brought this up before, lattice energy, and this is going to be the energy required to separate 1 mole of solid ionic compounds into their gaseous state. And so essentially we're going from a solid to a gas. So how much energy does it take to go from a solid to a gas? So we can give you an example of, like, let's say sodium chloride as a solid, and we're going to heat it up and add a bunch of heat to form sodium and chlorine. in a gaseous state. Now, we typically draw this as delta H, which is going to be our enthalpy of reaction lattice. And in this case, it's going to be positive 788 kilojoules per mole. And if we remember our delta H values, if we have a positive delta H value, that is going to indicate an endothermic reaction. So we have to put a lot of energy in. And so the more energy required, the greater the lattice energy, the more difficult it is to separate solids and gases. And this is going to kind of go along with our periodic trends and ideas as well. So magnitude of lattice energy depends on a couple things. And we have talked about these things already. I'm going to bring them up again. And it's going to depend on two things, generally. The first one is going to be the charge on the ion that we're separating out. And the second one is going to be the size of the ion, which is going to have an impact on it because of distance. And there's a formula that goes along with this. And we don't really use the formula, we just interpret the formula. And I'll talk about what I mean by that. So here's our energy. Energy, our lattice energy, is equal to K, which is going to be a constant. And I'm not going to worry about that constant right now. And it's going to be multiplied by Q1, Q2. And those are going to be our charges divided by distance. Okay? Now, how we can interpret this formula, and this is really what we do, is we just interpret this formula, is because the charges are the numerator of this, as charges increase, so if we have an increase in charge, meaning like we go from a positive 1 to a positive 2 to positive 3, that means we're going to have an increase in our lattice energy. Okay, because they're numerators in that formula, and in the distance, because the distance is going to be our denominator. As the distance increases, then that's going to cause a decrease in lattice energy. So let's give you an idea of what we're talking about here and put it to play, where we don't actually punch values into this formula, we actually just interpret the formula. Okay, so here's our example. It says it ranged from small to large with respect to lattice energy, and we're given 3 ionic compounds. So let's look at the charges first. And so sodium is going to be a +1, fluorine is going to be a -1, cesium is going to be a +1, iodine is going to be a -1. So we can't just look at the charges there. But calcium oxide has a 2+ and a 2-. So that's going to be the greatest charge differential. So that's going to be our greatest of these. That's going to have the greatest lattice energy. So now it comes down to sodium fluoride and cesium iodide. So if we follow our periodic trends, sodium and fluorine are both in period 3, and then cesium and iodine are way down there in period 5 or 6. I look at it, 1, 2, 3, 4, 5, 6, period 6. So we're going to see an increasing distance, larger atoms. And so when distance gets bigger, lattice energy gets smaller. So that's going to make cesium iodide the smallest, and sodium fluoride have a greater lattice energy because cesium iodide is the largest atom, and we have to look at distance. Okay, and that's how we take a look at that one. And so that is ionic compounds, a little bit of lattice energy, and a little bit of Lewis structures, which we'll be talking more about in the coming days, especially Lewis structures.